Okay, on Friday we were working on vector addition, and we kind of just got started on the vector component part of things, where we were starting to kind of get into using trigonometry to solve some of our vector addition problems. So that's what we're going to get into today, okay, full on into it. Reminder that this Friday you will have a quiz. Okay, you didn't have one last week because it was too short a week, but this Friday you will have a quiz. Okay, and during class today I will put up on the board over here on the right which practice quizzes you will probably want to have a look at through the week. Okay, so just a reminder, if I'm saying that, you're going, what practice quizzes? I don't remember any of that. Okay, in Google Classroom, hey, if you go to our class here, period 3, under class work, you will find a heading that says practice quizzes and solutions. Okay, we're in the kinematics unit right now. If you go into that, okay, what you will see is the first thing is a link to a playlist on my YouTube channel. Okay, that is where you will find the solutions. Okay, then you will find each numbered quiz here. Okay, after that, so this week I will tell you which ones are best for you to practice with. Okay, do a couple during the week, and then if you click on this, as I said, it'll go to the YouTube channel, and you just click on whichever one I told you to do, and you can watch the video of me doing the solution. So it'll walk you through. You can see if you did it right. If you're struggling with anything, then you know you should probably come in and see me at any of the many help times that are available, because I'm always here and having a life. Okay, you can come in and see me for help if you're struggling with something. Okay, but probably not a bad idea to take some time this week to work on whichever practice quizzes I put up on the board here for the week. Okay. All right, so back to vector addition. So key points for today, we got to look at how do we resolve a vector into its components. Okay, that is, how do you break it down into how far did this thing go horizontally and how far did this thing go vertically, just by using a little bit of trig. Okay, and then be able to use that to solve more complex vector component addition problems. Okay, also today, remind you guys, I will give you your formula sheets. Okay, I have those copied in ready for you today. All right, so to start out, let me ask you this. If I say that an object has gone 300 meters, 25 degrees south of west, okay, so they do this. They go 300 meters, that doesn't look like 25 degrees, but we're going to say it is 25 degrees south of west. Okay? If an object does that, do they go both south and west? Right? Like when they're done that, are they going to wind up both south and west of where they started? Okay. So if I know that they go 300 meters, if I know the magnitude of that vector is 300 meters, and I know the direction is 25 degrees south of west, could I calculate how far west and south they actually go? I could, because I have now made a right triangle, and I have the hypotenuse of that triangle, and I have an angle within it. So if I have those two pieces of information, I can calculate all the other bits of information about that triangle. Right? Like I could easily figure out that what this angle is just by going 180 minus 25 minus 90 and have that. Okay? I could also figure out these two sides. Okay? If I wanted to find out how far west they go, which trig function would help me do that? Cos. Okay. I would want to use cos because I know the hypotenuse of the triangle, and I'm looking for the side of the triangle that is adjacent to the angle. Okay. Remember that cos, okay, the cos of any angle, the cos of theta, is the adjacent side divided by the hypotenuse. Okay. In this situation, I know what theta is. It's 25 degrees. And I know what the hypotenuse is. It's 300 meters. Okay? So I know 2 out of the 3 parts of that equation. I could very easily solve for how long is the adjacent side. Everybody all right with that idea? It's a little bit of grade 10 trigonometry, okay, like SOHCAHTOA. You have to remember that. Okay? So knowing I could do that, could I also figure out how far south that person goes? Okay. Which trig function would I use for that? I use sine. I have the hypotenuse, and I'm looking for the opposite side from the angle, right? The angle is here, okay? So y would be the opposite side because it's not touching the angle. It's facing it, but it's not touching it. Okay, is that ringing a bell for everybody? The trigonometry part of that? Okay, because we're going to do this in no small exaggeration, a lot, okay, over the next 2 units. We're going to use this, what we're going to learn today, a lot. All right, so let's calculate how far west this particular object goes. So I want to calculate the adjacent side, or x. What do I have to do to this equation to solve for the adjacent side?
Substitute the information also cos of 25 over x over 300.
Sorry, over 300? Or if I want to find adjacent, what do I do with this?
Oh, I'm sorry, you bring it to the other side.
Exactly. I bring it to the other side. Right now I'm dividing by it. I would do the opposite, which is I would multiply it, right? If I want to move hypotenuse over to this side, I would multiply both sides by the hypotenuse. Okay? That'll leave the adjacent side over there by itself. Okay? Since I know the hypotenuse is 300 meters and I know theta is 25 degrees, all I have to do is punch those numbers in. So I would go cos of 25 degrees times 300 meters. Okay? And I would now be able to calculate just how far west, okay, that object actually goes. So I would just go cos of 25, close the brackets, times 300. Okay, so in doing that, that object is going to travel 271.89 meters west. There, they will end up that far west of where they started. Okay, so now I know this side. This starts 271.89. Okay, would I do a similar thing for y? Except I would use not cos but sine. Okay, so I would say, all right, the sine of 25 degrees. Okay, the sine of, that's too, we got going on 25. Sine of 25, okay, equals the opposite side over the hypotenuse. So I'd bring hypotenuse over and I would have the sine of 25 degrees times 300 meters equals the opposite side. So I can just punch that into my calculator. Sine of 25 times 300. All right, so they go 126.79 meters south. Okay, last week I said when you're drawing your vector diagrams, you don't have to measure, but your scale's got to be decent. Is my scale decent on this? What's the worst part of my diagram there?
Angle?
The angle, it's terrible. Okay, 25, that's probably more like 65 degrees. Okay, that's way bigger than 25, and as a result, it's giving me a misleading picture, right? I'm saying that y is 126 meters, and it looks like it's longer than the side that's 271 meters. That's where scale will come to bite you, okay, if you're doing a vector addition problem and you're not careful, okay, and you draw a sloppy angle like I just did, okay, then your picture will lie to you and your math will tell the truth, but you'll believe the picture. Okay, so just be careful with your scale. You don't want to end up having a crappy diagram like I just drew. Okay. All right, is that making some sense? How we would find those other sides? Okay, we're going to do a lot of that. Okay. All right. So what we just did, okay, is essentially what this slide is talking about. Okay, if I have vector A, that blue line there, okay, the hypotenuse of that triangle, and it's going north of east. Okay, then it's going to go somewhat east, that would be the AX, and somewhat north, okay, that would be AY. So the X and Y components of that vector. Okay? We say X and Y just because one's horizontal and one's vertical. It follows, you know, a typical math grid pattern. Okay, everybody all right with that? So as long as we know the angle and the hypotenuse, which we would know because any vector quantity has to have both magnitude and direction, we should be able to solve for its horizontal and vertical components anytime. Okay? So what we just did is we broke that down and we said, all right, I know what A is, I know what theta is, so if I want to find the x component, I'm going to use cos, because in this situation, the x component is adjacent to the angle. Okay? And I want to find the y component. In this case, the y component is opposite, so I would use sine. Is y always going to be opposite? Not always. Okay, don't memorize that y is always sine, x is always cos. It's not. Every triangle is going to be different. Okay, so you just kind of have to analyze as you go. All right, everybody okay with what we did there? That's just that basic kind of Math 10C geometry. All right, so if we had this hypothetical vector that was 175 meters long, so that's D, okay, the blue line there, okay, is 175 meters long. Okay, and is 50 degrees, okay, relative to the, it should say positive x-axis. So relative to the positive x-axis, okay, find the x and y components. Why is it such a big deal to say relative to the positive x-axis?
Otherwise it would be upside down.
Could be upside down, or could be
Oh, yeah, sorry.
backwards, right? It could be above the negative x-axis and be pointing the other way. Okay? Could be, if I don't say above, then it could be below it. It could be pointing downwards. Okay? So we do have to specify. Whenever we give that angle, it could be north of east, or east of north, or above the positive x-axis, or below the negative x-axis, or left of the positive y-axis. Okay? You have to kind of interpret those and draw them on that grid. Okay? All right, so if I want to find x here, okay, is that adjacent or opposite the 50-degree angle? Okay, it's adjacent, it's touching it, okay, it's beside it, that's adjacent. I would use
Not sine, sorry, cosine.
cosine, right, because it's adjacent. Cosine uses adjacent and hypotenuse to calculate. Okay, if I want to find y, it's opposite this angle, okay, so I would use sine. Okay, I have the angle and I'm looking for the opposite side using the hypotenuse. Okay, so that's what we're doing here. Okay, if I wanted to find y, I would take d, multiply it by the sine of the angle, so 175 times the sine of 50. That tells me that y is 134 meters. Okay, and then for x, because it's the adjacent side, okay, I would go d cos of theta, 175 times the cos of 50, and I find that that side is 112 meters. Okay, so now I've resolved that into its components. Everybody okay with that process? Yeah, go ahead, yeah. Why would we ever need to do that? Why would I want to break down a vector into its components if I already know its magnitude and direction? Well, the answer is if I need to put it together with another vector. Okay, so if I had a situation like this, okay, where let's say I'm given a vector that is 12 meters, okay, and it's 15 degrees south of east. Okay, so an object goes there. It goes 12 meters, 15 degrees south of east. And then it turns and travels 20 meters at, let's say, 40 degrees east of north. So then I have a new vector, okay? So I have 20 meters. What did I say? I said 20 meters and I said 40 degrees, right? Okay, so 20 meters, 40 degrees east of north. Find the total displacement. Well, I can't just add 12 and 20, can I? Right? That would give me the total distance traveled, but it doesn't give me the displacement. Okay, if I have these two vectors, where would I draw a line that represents my total displacement?
From initial point and final?
Right, I need to connect my initial position and my final position. So that means I need a line that goes from here to here. Okay, so that line there would represent my change in position, my total displacement. And it would have both a magnitude, how big is it, and a direction, which way does it point? Agreed? Okay. So if that has a magnitude and a direction, can I make a right angle triangle out of it as well? Right? That object, over the course of that trip, ends up north and east of where it started. How am I going to find out how far north and east it ends up? I know nothing about that line, except that it goes north and east. Okay. Well, let's look at this. If I take, can I find out how far east the red line goes? Can I find out how far south the red line goes? Okay. Can I do the same with the black line? I can. If I take how far east it goes during the red vector and how far east it goes during the black vector, if I add red x and black x, do I get what purple x would be? That's why we break vectors down into their horizontal and vertical components. Okay? I have to figure out, in this one, I can figure out how far south and east it goes. And in this one, I can figure out how far south and east or north and east it goes. Then I can put them together to get a picture of the whole trip, okay? Which is exactly what I'm going to do here. If I find red x and black x and add them together, I get purple x. If I take red y and black y and add them together, I'll get this, because one is south and the other is north. So if I put them together, I'll get purple y. Okay? This is vector component addition. I break down the vectors I have into their components, and then I add the components together. We say add, okay? I realize that one is south and one is north, but south would be negative. Okay, so I'd be adding a negative or subtracting, whichever makes more sense to you. Okay. All right, so let's maybe walk through this one. How would I calculate red x?
Cos?
Yeah, I'd use cos. It's adjacent to that 15-degree angle, and I know the hypotenuse of that triangle is 15 meters. Okay, or sorry, 12 meters. Okay, so to find red x, because it's the adjacent side, I would take the cos of 15 degrees, and I would multiply it by 12 meters, the hypotenuse. Right? All I'm doing here is going cos of theta equals adjacent over hypotenuse, and I'm just manipulating for the adjacent side. I'm multiplying the hypotenuse over. Everybody okay with that? Okay. All right. So when I do that, okay, so cos of 15 times 12. All right, we got 11.59 meters. Okay, and that's actually going to be east. Okay. Now, I'm only going to write a couple of decimal places on the board, but I'm going to keep all of the decimals in my calculator, and you must do the same. Okay, we talked about significant digits there on Friday. Okay, we don't do any rounding off until we're done the question. We carry everything, every single decimal, all the way through a problem. And at the very end, I go, okay, now I got to round. Now I got to do this. Okay, so I keep every single decimal place all the way through. Okay, so I've got x. I know that in the first vector, okay, I go 11.59 meters east. Okay. I also need to figure out how far south I go. Okay, y in that triangle anyway is opposite that 15-degree angle. Okay, so if I'm using the opposite side and the hypotenuse, I use sine. Okay, so I would go sine of 15 degrees times 12, and that'll tell me how far south we go during that part. So sine of 15 times 12. All right, so 3.11 we'll say. Okay, why am I putting the east and the south in there? Right. Later, when I put them together, when I add the two y's together, if I see that one y is north and one y is south, I know that one of them has to be negative. If they both ended up north, then I just add them. I wouldn't worry about it. Okay. Got to do the same thing with the black triangle. Okay. Oh, sorry. I know that red y is 3.11 meters. Okay, and it's south. All right. Let's look at the black triangle now. Okay. So if I'm looking for black x, adjacent or opposite my 40-degree angle? Right, a 40-degree angle is here, x is way up here. Adjacent or opposite? Opposite. Okay, remember I said don't memorize that x is always cos, because it's not. Here, it's going to be sine. It's the opposite side. Okay, so I know in this triangle, the object goes 20 meters, 40 degrees east of north. Okay, so I'm going to say that x, being the opposite side, can be calculated by taking the sine of 40 and multiplying it by the hypotenuse, 20 meters. Okay, again, all I'm doing here, guys, is going the sine of theta equals opposite over hypotenuse, and I'm just manipulating for that opposite side, right? Because I have the angle and I have the hypotenuse. Okay. Okay, so sine of 40 times 20 meters. Okay, so 12.86 meters, we'll say. Which direction is that? East. Yeah, right? We said it was 40 degrees east of north, then they're definitely going east, okay, along the x. All right, well, that's good news because my other x was also east. Okay, so it just goes east. I don't have to worry about any wests or negatives here. All right. The y, black y, is touching that 40-degree angle. That makes it adjacent. So I'm going to use cos. Cos of 40 degrees times the hypotenuse, 20 meters. And so cos of 40 times 20. All right, so that side is 15.32 meters. Which direction is that one going? North. Yeah. Okay, it's going up on the page, that's north. All right. I've found all the x's and all the y's now for the vectors I was given. Can I now find purple x and purple y? I can. Okay. I know how far over and down and over and up my other vectors went. And if I put red x and black x together, right, if I take that side, oops, not what I wanted. Okay, if I take that side, right, and add it to black x, that makes purple x. Okay, everybody okay with my geometry there? Okay, so I'm just going to take, oops, that's not what I wanted. Okay, I'm going to take black x and red x, and I'm going to add them together to get purple x. And so purple x is going to be 11.59 plus 12.86. I'm only writing those decimals, but luckily for me, I have all the decimals still stored in my calculator. All right, so I'm just gonna go up, and I'm gonna grab the 11.59 and the 12.86, sorry. Okay, so in total, over these two parts of the trip, the object ends up 24.45 meters east of where it started. Okay? Purple X, how far we went east and over the whole trip is 24.44 meters. That line there is 24.44 meters long. 24.45. Okay? And it's east. Okay? Now, in the first y vector, in the red vector, we actually ended up south. But in the second one, we went north. Did we end up going more north than south over this whole trip? That's what the diagram says. Okay? So hopefully the math is going to agree. Okay? When I want to find purple y, I'm going to add together red y and black y. Okay? But I'm going to make sure that red y is negative. Okay, so purple y, okay, is going to be negative 3.11 plus 15.32. Okay, those are my two y's. So negative 3.11 plus, whoop, I shouldn't do it that way. Okay, I'm going to go negative and grab that 3 point. Keep all my decimals. Okay, and then add that to the 15.32. Okay, so in total, over this whole trip, we ended up 12.2 meters north of where we started. Okay, so I'm going to go and put that on my diagram. Oh, too far. Okay, so I went north and I went east. Do I now have two sides of that big purple triangle? Can I figure out how far it is between my start and my finish? How do I do that? Tangent will get me the angle, which I'll need eventually, but I want to figure out first how far. I want to find the magnitude. How would I do that?
A squared plus b squared equals c squared.
Right, use Pythagoras. I now know two sides of that triangle, so I can use them to figure out the hypotenuse. A squared plus b squared equals c squared. Okay, so that'll be my next step. If I want to find my, what we call resultant displacement or total displacement, I'm just going to use Pythagorean theorem with those two numbers I just spent all that time calculating. Okay, so I'm going to say that d will equal the square root of 12.22 meters squared, actually I won't put the meters in there, and 24.45 squared. Okay, and once again, I want to use all of my decimal places. So I'm going to go to that number, squared, go up to that number, squared. Okay, whoop, oh, I multiplied them. That's not what I wanted to do. 12.221 squared plus, yeah, that number was way too big. Squared. Better. Okay, so now we know that in total, our total displacement's magnitude is 27.33 meters. Okay, so I can go back to my diagram and go, all right, I know this line here, okay, is 27.33. All right, my displacement's got a magnitude. What else does it need? Direction. Can I find that now? Could I use any trig function I wanted at this point? I could. I know all three sides of that triangle. So you got a favorite? Fire away. Okay, my favorite is 10. You guys know that already. Okay, so I'm going to just take my adjacent side and my opposite side, and I'm going to use tan to figure out what this angle here is, because that'll be the direction that the object was going. How did I know to find this angle as opposed to that one?
Because that's the one where you started.
Yeah, I need the angle that says you started here, this is the direction to go from where you started. I want the angle that points from beginning to end. That angle tells me how to get back. I don't want that one. Everyone follow me there? If you're ever uncertain as to which angle to find, draw a circle around your starting point, and wherever that circle goes through your triangle, that's the angle to find. Okay? All right, so I'm going to find that angle there. So I'm just going to go tan of theta equals the opposite side. So that'll, and actually, sorry, I'm going to go inverse tan. Okay, of the opposite side, so the 24.45 divided by 12.22. Okay, and that'll give me the direction I'm going. And I will use all my decimals. So second tan of 24 divided by 12. Okay, so we're looking at a 63 degree angle there. 63.45 is what I'll write. Okay, was my diagram reasonably to scale? Right? Like my picture's not lying to me, is it? Right? It looks about right for the math I've got. Okay, always a good thing. All right, so I've got an angle, I've got a magnitude. I'm almost done. I just need an answer with the right number of significant digits. How many significant digits should my answer have? 2. Every single number I gave you had 2. Okay, so my final answer should have 2. So my final answer after all of this, okay, is going to be that the total displacement is 27 meters at 63 degrees. Which direction? Other way. East and north, right, because remember my angle's touching north and going east and north. It takes a while to get the hang of that. Okay, is that a lot of work? I mean, that question there took us, 22, 23 minutes. Are they always going to take you that long? You guys will do enough of these that you'll be doing these in like 8 minutes, 10 minutes. Okay. How do you get faster at these? I wish there was another answer, but it's strictly practice. And we're going to spend a lot of time working on these over the next while. Okay, so if you looked at this right now and you're just like, oh my God, I'm deer in the headlights, it's okay. Okay, most people are the first time we go through it. Here's the good news. The steps I did there are always the same. You will always do those steps. Okay, you'll draw your diagram. You'll identify your X's and your Y's. You'll calculate your X's and your Y's. You'll add your X's, you'll add your Y's. You'll do Pythagoras, you'll do some trig, and you'll be done. Okay, it's always the same steps. Trickiest part, drawing the picture. Okay. All right, so here's all the stuff we just did, but in a way better diagrammatic fashion than I draw it because I can't draw. Okay, so if I've got two vectors, A and B, okay, and they go together, I know that if I find their components, okay, and I put their components together, I will get the totals for my whole trip. Okay, and that's what we did there. We found the X's, we found the Y's, okay, we put them together, so AX and BX made the whole thing, okay, AY and BY added up to CY, okay, and we just went from there and drew the final picture. Okay, always going to do it that way because we always draw vectors tail to head, okay, just exactly how I drew them, okay, in that diagram on the last page, right? When I first started that out, I drew the red vector, and then I drew the black vector tail to head. Okay. I want you guys to write this one down, okay? And then we're going to try it together. Question for Go to Washington? Okay. Okay, so line C represents the total displacement over the whole trip. Okay, I've drawn those vectors tail to head, okay, and I've drawn their right triangles. Okay, so I know that A goes north and east, and I know that line B goes east and south. Okay, everybody with me so far? All right. Here's what I want you guys to do, okay? First off, put that diagram in there so you've got it, because it goes with this question and it's important, okay? And then I want you to calculate AY, AX, BX, and BY. Okay, so find the X and Y components of both of those triangles using trigonometry. Okay, give you a few minutes to get ahead of me, and then I'll walk through that process. Let's walk through finding the X's and Y's here. Okay, so in the blue triangle, okay, for triangle A, if I want to find the Y component, so blue Y, okay, what trig function am I using for that side? Cos, because it's adjacent to the 20-degree angle that we drew. Right, so I'm going to go cos of 20 degrees times the hypotenuse, which we were told was, I don't have it written on here, was 145 meters. That was 105. Okay, so if I'm trying to find blue Y, okay, I'm going to multiply that by 145. Okay, so I'll have cos of 20 times 145 is going to give me 136.255 meters, and that is north. Okay, X in that blue triangle is opposite the 20-degree angle, so I'll solve for that using sine. I'll go sine of 20 times 145 meters, okay, because that's the hypotenuse. Okay, that's going to be 49.593 meters, and that is east. Well, actually, it's along the x-axis. We're just going to use east for this. Okay. Am I good with that triangle? Right? I know all the sides of that triangle now. Can I do the same thing for the yellow triangle? Okay, and I have to. All right, so for the yellow triangle, okay, yellow X, okay, is adjacent to the 35-degree angle, so I'll go cos of 35 times 105 meters. Okay, so that's going to be 86.01 meters. That's pointing east. Right, and then Y is going to be the opposite side, so we'll go sine of 35 times 105. And so 60.226 meters. That's so. All right, so now I've got all the sides, yes? I'm trying to find C, magnitude and direction, the red line, all right? If I now know all of these sides, can I take AX and BX and get CX? Can I do the same thing with the Y's? Yeah, if I take AY and BY, what I'll be left with is CY. Everyone okay with that idea? Okay, so As long as I keep in mind that for my y components, one is down and one is up, I'm okay. Yep. Right? And then I would do Pythagorean theorem and trigonometry, because I need magnitude and direction to get theta. Now, if you drew the red triangle this way, is that okay? It is 100% okay. You're just going to get the opposite angle. I'm going to get north of east. You're going to get east of north. Totally fine. Only reason I drew the triangle this way is now my lines don't overlap. Okay, I hate it when all my triangles get all messed up and they're all overlapping each other. And so I try my best to draw them in a way that makes them not overlap too much. Okay, we are getting close to being out of time here, guys. We got about 3 minutes. So let's see if you can get CY, CX, and C before, in the next 2 minutes. We're gonna go over it tomorrow, don't panic, okay? But we gotta go over and do the opening assembly here. Yep. Yep. Make sure they have the same number so you can complete it. So I think everything has 3. So that should also have 3. Yeah.
The only thing that I'm struggling with still is the direction.
Okay.
Like,
Yeah, right. So for this final triangle here, we draw like this. Okay. This is the angle you start here. Okay. So the way you say whether it's from east to east or north, just whatever it's touching due east. So
if there's either one,
that's right. I'm going that way from
the opposite of what you think you're doing. Just touching it from the other side.
Yeah.
That's the only thing I think I'm messing up.
Because you could also write it from this, right? Measure the north from east.
Okay.
Yeah.
Thank you.